Okay, this is Algebra Lesson 6. Are there any questions about homework or anything that we did on group theory so far?
Hello, Professor?
Yeah, go ahead.
Okay, so from the homework, could you go over 2B, 3B, 5A, and C?
Two
2B.
on linear functions?
Yeah.
Yeah, sure. Okay. So,
Sorry, Professor, and number 5 and 7, please, when you get a chance.
yeah, of course. So let's start with number 2. We are homework 2, number 2. So L is the set of linear functions. So f of r means functions from the real numbers to itself, and linear means f of x is of the form ax plus b. So you can certainly add, if you have f of x is ax plus b and g of x is cx plus d, when you add them, you get ax plus b plus cx plus d, and you can collect the terms like this: a plus c times x plus b plus d. So this is again a constant times x plus a constant, so it's another linear function. So this is an L. So L is closed under addition of functions. So L is a semigroup. Now, under addition. In fact, it's also a group under addition, but I didn't ask you to check that. But there's another operation that you can perform on functions, which is composition of functions. So if we start with these two functions, f and g, what is f composed with g? This is f of g of x. That means f of the number cx plus d, because g of x is cx plus d. And what does f do to a number? It multiplies it by a and adds b. So this is a times cx plus d plus b. And again, if you rearrange this, expanded, this is ac times x plus ad plus b. So again, this is a constant times x plus a constant. So f composed with g is also an L. So this proves that this L, the set of linear functions, is a semigroup under not just the operation of addition, but also under the operation of composition. And a general fact that we proved is that composition of functions, any kind of functions, is always associative. So this property of composing functions is an associative operation on this set of linear functions. And so that proves that L is a semigroup. Okay. Any questions about that? Does that make sense?
Yeah, makes sense.
Someone also asked about question 5. Is that right?
Yes, 5 and 6.
So number 5 is to show certain sets are or are not groups. So the first set is all complex numbers of absolute value equal 1. Let me just call that T to give it a name. And there's a nice picture. This is just the unit circle. If you take Z equal X plus YI in the complex numbers, the absolute value of Z is the square root of X squared plus Y squared. And that's equal to 1 if and only if X squared plus Y squared equals 1. So the set of complex numbers with absolute value 1 is the set of points on the unit circle. And how do we prove it's a group? Well, let me give you 2 ways. So prove T is a multiplicative group. So absolute value of complex numbers, just like absolute value of real numbers, satisfies the multiplicative property that if you have 2 complex numbers, Z and W, the absolute value of the product is the absolute value of Z times the absolute value of W. And if Z is not 0, then the absolute value of W over Z is the absolute value of W over the absolute value of Z. This follows from this, but I'm just writing it down explicitly. So if Z and W are in this circle, T, then the absolute value of Z and the absolute value of W are both equal to 1. And that implies the absolute value of Z times W is the product of the absolute values. That's 1 times 1, which is 1. So if Z and W are both in T, then Z times W is in T. So T is closed. Under multiplication. And it's true also that multiplication of integers, fractions, rational numbers, real numbers, complex numbers, no matter what their absolute value, is associative, right? That is, if you have Z1, Z2 times Z3, that's Z1 times Z2, Z3 for all complex numbers. So this set T, complex numbers on the unit circle, closed under multiplication, it's associative. The absolute value of 1 is 1, so 1 is in here. That's just this point. That's the complex number, or 1. This is 1 plus 0 times I, if you like. And if Z is in T, then the absolute value of 1 over Z is the absolute value of 1 over the absolute value of Z. That's 1 over the absolute value of Z. But the absolute value of Z is 1, 1 over 1, which is 1. Which means that 1 over Z, or Z inverse, is also in T. So this set T is closed under multiplication. Multiplication is associative. It contains the identity. The multiplicative identity is the complex number 1, and it contains the inverse of all of its elements. So T is a group. Are there any questions about that? I mean, that's the proof of 5a. What about 5b? Suppose you take the circle of radius 2, all complex numbers with the absolute value of z is 2. So this is 2 minus 2, 2i minus 2i. So 2 is certainly in this set. Let me call it, I don't know, T2. 2 is in T2. But 2 times 2, which is 4, is not in T2. Because 4 has absolute value 4. It doesn't have absolute value 2. So T2 is not closed under multiplication. So not a group. Any questions about this? What about 5C? And that in 5C, we take T, I'll call it T2, T3. So this is all Z, all complex numbers Z, where the length of Z is 2 to the K for some integer K. So for example, when K is 0, 2 to the 0 is 1. That's the circle of radius 1. When K is 1, 2 to the 1 is 2. That's the circle of radius 4. When K is minus 1, 2 to the minus 1 is a half. That's the circle of radius a half. When K is minus 2, 2 to the minus 2 is a fourth. That's the circle of radius a fourth. So this is the union of infinitely many circles. And why is this a group? Well, if you take Z and W to be in this set, then Z is 2, has the absolute value of Z is 2 to the K for some K. The absolute value of W is 2 to the W for some W. So the absolute value of the product is the product of the absolute values. That's 2 to the K times 2 to the W, which is 2 to the K plus W. So this is again a power of 2. So this is in the set. So the set of numbers that lie on the union of this infinite collection of circles is closed under multiplication. It's not closed under addition, but there's no addition in this problem. It's closed under multiplication. And again, multiplication is associative. 1 is in this set because the absolute value of 1 is 2 to the 0. And if Z has absolute value 2 to the K, then Z inverse, which is 1 over Z, has absolute value 1 over the absolute value of Z, which is 1 over 2 to the K, which is 2 to the minus K, which is again 2 to a power. So this set, which is a union of circles, is closed under multiplication, contains the identity, contains the inverse of each of its elements. That's what we need to show. Let's see. So there are questions about this? This is part of learning how to prove stuff.
Professor, can you move your paper? I just want to sit down.
Sorry?
Can you move the paper a little bit high? No. Up.
Sorry, what are you asking?
I'm asking if you can move your paper.
Move the what?
Move your paper up.
Like this?
Yeah.
Sure. All right. I think someone also asked about question number 6.
Number 7.
Okay, then I'll do both 6 and 7 because they're both important.
Okay.
So number 6, remember the definition. H is a subgroup of a group G if it satisfies the following 3 properties. First, the identity in the group. So if E is the identity element in G, then E is also in H. Second, if X and Y are both in H, then their product is in H. So H is closed under multiplication. And if X is in H, then X inverse is in H. So that's the definition of a subgroup. So we have to prove that H is a subgroup if and only if a certain condition is satisfied. So this means we have to prove 2 things. If H is a subgroup, then the condition is satisfied. And if the condition is satisfied, then H is a subgroup. So suppose, first of all, H is a subgroup. And let X and Y be 2 elements in H. Then, first of all, Y inverse is in H by property 3. Property 3 says the inverse of every element of H is in H. And so XY inverse is in H by property 2, which says H is closed under multiplication. So if X is in H and Y inverse is in H, then XY inverse is in H. So that was half of what we have to show. If H is a subgroup and XY is in H, then XY inverse is in H. I should also say, suppose H is a subgroup. So then E is in H. So H is not the empty set. H is not empty and is closed under this operation. Okay. What about the converse? So that H be a non-empty subset of G such that whenever X and Y are in H, then XY inverse is in H. That's the condition. Must show H is a subgroup. So H non-empty, that's part of our assumption, implies there exists an element A, X in H. H contains something. So because x is an h and x is also an h, I just apply this condition with x equal to y. This means x times x inverse is an h. But x times x inverse is the identity. So H contains the identity. So the first condition of a subgroup is satisfied. Suppose Y is in H. So then, because X is in H, if we apply this condition with X equal to E, E times Y inverse is in H, which means Y inverse is in H. So H contains inverses, contains the inverse of each of its elements. And finally, we want to show that H is closed under multiplication. So that X and Y be in H. Then Y inverse is also in H. And if I apply, again, this multiplication condition to X and Y replaced with Y inverse, so X, Y inverse inverse is in H. But the inverse of Y inverse is Y. So this says XY is in H. So if H is a non-empty set that satisfies this property, then H is always a subgroup of the set of the group G. So again, this is the sort of thing, it's not a long proof by any means, but it's very important to understand this kind of algebraic argument. Okay, number 7. Suppose X is in a group and X to the n is the identity. So X to the n is the same as X to the n minus 1 times X. And it's also the same as X times X to the n minus 1. And that's equal to E. So if I let Y equal X to the n minus 1, just to make this a little clearer, perhaps, this says Y times X and X times Y is equal to E, which is the definition of Y being the inverse. So Y is X inverse. That means X inverse is X to the n minus 1. And that's the whole proof. Other questions?
Could you do 3?
Okay, so number 3, in the complex plane, this is 1. These are points on the unit circle. 1, I, minus 1, minus I. And so you remember I squared is -1. I cubed is I squared times I, which is -1 times I, which is minus I. I to the fourth is I squared times I squared. -1 times -1 is +1. And of course, I to the 0 is 1. So this set, 1I minus 1 minus I, is the same as the set 1I, I squared, I cubed, where I to the fourth equals 1. So this is closed under multiplication. All right, if you take I to the K, I to the L, that's I to the K plus L. So this is closed under multiplication. And -1 times -1 is 1. So the inverse of -1 is -1. I to the fourth is 1, which is the same as I times I cubed, or I times minus I, or minus I times I. So the inverse of I is minus I. And so the inverse of minus I is I. I mean, this set is closed under multiplication. It contains the identity, and it contains the inverse of each of its elements. Right? If you wanted to make a table, X and X inverse, 1I minus 1 minus I. The inverse of 1 is 1. The inverse of I is minus I. The inverse of -1 is -1. The inverse of minus I is plus I. Every element has an inverse. So this set consisting of 4 complex numbers is a multiplicative group. What about the set consisting of 1 minus a half plus I times √3/2 and minus a half minus I √3/2? So you can check each of these numbers has absolute value 1. This is 1. This is minus a half plus I √3/2. This is minus a half minus √3/2. So these are exactly the points on an equilateral triangle inscribed in the unit circle. I mean, that's what they look like. I mean, these points, are, from calculus. This comes from the sine and the cosine of 2π/3 and 4π/3. Okay? And you can check. So let me call this rho. And if I were to take rho and square it, I would get this. So this is the set 1 rho squared, where this is rho squared is this. You multiply this number, you see that you get, and rho cubed is 1. So this set is closed under multiplication. Like, for example, what is rho squared times rho squared? It's rho to the fourth. Rho to the fourth is rho times rho cubed. Rho cubed is 1. So rho squared times rho squared is rho. This set is closed under multiplication. And so you have a set of complex numbers that contains the identity, closed under multiplication. Rho times rho squared and rho squared times rho, they're rho cubed, which is 1. So the inverse of rho is rho squared, and the inverse of rho squared is rho. So this is a little bit of elementary geometry and complex numbers and group theory. Any questions about this? Oops. This wasn't number 7. Sorry, yeah, that was number 7. This is number 3. A, B. Number 3C. We have a set of 6 complex numbers, and they are exactly the points of a regular hexagon inscribed in the circle, right? I mean, you know, if you take the angle pi over 3, cosine of pi over 3 is a half, sine of pi over 3 is root 3 over 2. The complex number 1/2 plus root 3 over 2i, that's this guy. This angle is pi over 3. Let me call this, I don't know, alpha. Then this number, minus a half plus root 3 over 2i. If you square alpha, this is what you get. It's alpha squared. This is minus 1, which is this number cubed. This is minus a half minus root 3 over 2i, which is alpha to the 4th. This is plus a half minus root 3 over 2i, which is alpha to the 5th. And alpha to the 6th is 1. So when you draw these 6 complex numbers, they're the vertices of the regular hexagon inscribed in a circle in the complex plane. And so this set really is the set 1 row, row squared, row cubed, row to the 4th, row to the 5th. That's what this set is. Where alpha where alpha to the 6th is 1. So it's just a set of powers, alpha to the k times alpha to the l. That's alpha to the k plus l. What is that? Well, it's alpha to the k plus l. If k plus l is in most 5, k and l are between 0 and 5. And if it's bigger than 6, it's alpha to the k plus l minus 6. If k plus l is greater than or equal to 6. And the inverse of alpha to the k is alpha to the 6 minus k. Because alpha to the k, alpha to the 6 minus k, you add exponents, that's alpha to the 6th, which is 1. So again, if you're not used to complex numbers and thinking about complex numbers geometrically is drawing the complex numbers in the plane, this is a good exercise to give you some practice with that. Okay. Any questions about this?
Question, Professor.
Yeah.
So if I wanted to find more practice questions, it would just be complex numbers and complex numbers in the plane.
Well, on what I just did, yeah.
Okay, gotcha.
Yeah. Mm. Okay, so we were talking about groups, and two important classes of groups are permutation groups and matrix groups. And let me say a little bit about both of these. So Sn, which is called the symmetric group, n's a positive integer. So this is the set of permutations of the numbers 1, 2, 3 up to n, the whole numbers, the positive integers from 1 to n. And a permutation of any set x, this is my set x in this case, the first n permutations, is a function, say sigma from x to x, that is 1 to 1 and on to. So 1 to 1 means if you have an element that goes to something over here and an element that goes to something over here, this is just a function from x to itself. If these points are different, then these points are different. You can't have two different elements of x being sent by this function to the same element of the set x. And onto means for any element y in x, there's always an x in x, where sigma of x is equal to y. And the standard form for a permutation sigma in Sn is the following. You can write this as a matrix with two rows. In the first row, you write the numbers from 1 to n. In the second row, you write your permutation of those numbers. So A1 is sigma of 1. A2 is sigma of 2, and so forth. This just tells you where each of these numbers is mapped to by the function. So for example, if n is equal to 3, we're looking at permutations of 1, 2, and 3. Suppose sigma is the permutation 2, 3, 1. So this says sigma of 1 equals 2, sigma of 2 equals 3, sigma of 3 equals 1. And if you want, you can sort of draw a picture of that. This is 1, 2, and 3. Sigma sends 1 to 2. Sigma sends 2 to 3. And sigma sends 3 to 1. So it's a kind of a cycle. And what would the inverse of sigma be? Well, if sigma sends 1 to 2, then the inverse should send 2 back to 1. If sigma sends 2 to 3, the inverse should send 3 back to 2. And if sigma sends 3 to 1, the inverse should send 1 back to 3. So this, the picture for this might be 1 goes to 3, 2 goes to 1, 3 goes to 2. It's kind of like the cycle in reverse order. Mm-hmm. And permutations can be a little bit complicated. Suppose I take a permutation in S5. So maybe 1 goes to 4, 2 goes to 5, 3 goes to 1, 4 goes to 3, 5 goes to 2. That's a permutation, right? Sigma of 1 is 4, sigma of 2 is 5, sigma of 3 is 1, and so forth. Let's see. You can't always draw nice pictures of these things, but let's see. So 1 gets sent to 4. 2 gets sent to 5. 3 gets sent to 1. 4 gets sent to 3. And 5 gets sent to 2. So that's kind of a picture of this permutation, but it's a little bit confusing with all those lines. But if you look at it, you see that this is like a little cycle just by itself. 2 goes to 5, goes back to 2, and 1 to 4 to 3. So if I put the points down in a different order, say 1, 3, 4, 2, 5. So 1 goes to 4, 4 goes to 3, 3 goes back to 1, 2 goes to 5, 5 goes back to 2. So these are both sort of graphic representations of this permutation, but this picture is a little bit cleaner. Let's see. Let's just make up one at random and see what kind of pictures we can draw. And I'll just write down some random permutation. Let's see, what numbers am I missing? I have 1, 2, 3, 4, 5, 6. I need a 7 and a 9. Okay. So that's a permutation. And if we want to draw it, if I just wrote down 10 dots at random, it'd be kind of confusing. But let me just start with like the number 1 and follow it around. So let's see. 1 goes to 10. 10 goes to 7. 7 goes to 5. 5 goes to 6. 6 goes to 2. 2 goes to 8. 8 goes to 4. 4 goes to 3. And 3 goes back to 1. And the only thing I haven't touched is 9. And 9 just went to itself. So this permutation consists of like a long cycle of 9 numbers in this order. And then this one sort of outstanding guy. Let's try another one sort of at random. Just kind of interesting to see what happens. Let's see, I have 1, 2, 3, 4. Yeah, I think I have every number once. So let's look at this permutation. So this is also a permutation in the symmetric group S10. So if I just start with the number 1, say, and follow it around, 1 goes to 2, 2 goes to 7, 7 goes back to 1. So that's a little 3 cycle. There are 3 numbers in this cycle. And I've used 1, 2, and 7. So let's see, what about 3? 3 goes to 8, 8 goes to 9, 9 goes to 4, and 4 goes back to 3. So I could call this a 3 cycle because there are 3 numbers in it. And I could call this a 4 cycle. And I'm missing what numbers? 1, 2, 3, 4, 5. Okay, 5 goes to 10. 10 goes to 6. And 6 goes back to 5. So this permutation decomposes, in a sense, into these 3 cycles, one of length 3, one of length 4, and a second one of length 3. Let's see, this was a 9 cycle up here. Because there were 1, 2, 3, 4, 5, 6, 7, 8, 9 different numbers in it until it comes back on itself. Okay, any questions about this? So these cycles are really fundamental. They're one of the building blocks of permutations. So let's give them precise definition. So a K cycle in the symmetric group Sn is a sequence of K distinct integers, A1, A2, A3 up to A sub K. They're pairwise distinct. I'll write them like this. I'll say it's more than a sequence. I say a K cycle in Sn is a permutation of K integers, which we write like this. And what we mean by this is that this permutation, just call it alpha. This is the permutation such that A1 is sent to A2, A2 is sent to A3, A3 is sent to A4, and so forth. A sub K minus 1 is sent to A sub K, and A sub K goes back to A1. So you can really think of this as a picture in a circle. So the permutation sets each number to the next one around it in the circle. And when you get to AK, that comes back to the starting point. So it's called a cycle because you can think of this as a circular permutation. And so this alpha is a permutation in Sn. And if B is any number from 1 up to n, and B is not equal to any of the numbers A1 up to A sub K, then alpha of B is just equal to B. It doesn't move. So this cycle is defined as it's a permutation on K different numbers, and it moves each to the next one in the sequence and then back to the beginning. And for any number that's not in the sequence, alpha doesn't move it at all. Alpha is any other number, B is fixed. And there's an important theorem that says every permutation in Sn, for every n, is a product of cycles. And not just, it can be more precise, disjoint cycles. So what does it mean for cycles to be disjoint? Suppose alpha This is a K cycle in Sn. And say beta up to BL, this is an L cycle in Sn. So alpha and beta are disjoint, means the numbers here, the A's are different from the B's. If AI is different from BJ for all I and J. So for example, alpha equals 1, 2, 3, and beta equals 4, 5, 6, 7 are disjoint cycles. Now remember, in Sn, the group operation is composition. See, a permutation, again, it's just a function, a one-to-one and onto function from the set to itself. So the group operation is composition of functions. So what is alpha times beta? So this is going to be a permutation that's, say, in S7, right? Because these are permutations of the first 7 integers. And if I write it in the standard way, let's see, beta of 1, there's no 1 here, so let's just see. Alpha beta of 1, this means alpha of beta of 1. But 1 is not one of these numbers, so beta of 1 is 1, and alpha of 1 is 2. Alpha beta of 2 is alpha of beta of 2. There's no 2 here, so beta of 2 is 2, and alpha of 2 is 3. Alpha beta of 3 is alpha of beta of 3. There's no 3 here in beta, so beta of 3 is 3, and alpha of 3 is 1. Alpha beta of 4 is alpha of beta of 4. Beta of 4 is 5. And alpha of 5, there's no 5 there, so alpha of 5 is 5. So this is 5. Alpha beta 5 is alpha of beta of 5. Beta 5 is 6. Alpha of 6 is 6. And similarly, if you check, alpha beta of 6 is 7, and alpha beta 7 is 4. So the product of these two disjoint cycles is this.
Professor, could you repeat this part again?
Well, okay. So alpha is a 3 cycle. Beta is a 4 cycle. And they're disjoint because the numbers here are different from the numbers here. There's no common number. And alpha sends 1 to 2, 2 to 3, 3 to 1. And alpha sends 4 to 4, 5 to 5, and so forth. Alpha only moves the numbers that are in the cycle. And in the same way, beta only moves these 4 numbers. So if I want to compute alpha beta of 1, right? So composition of functions, alpha beta of 1 means alpha of beta of 1. Beta of 1 equals 1, because there's no 1 there. So this is alpha of 1, and alpha of 1 is 2. Let me do a few more examples just so you get to see composition of permutations or multiplication of permutations in a lot of different examples. So let's take permutations in S5. So suppose sigma, if I write this in standard form, 1, 2, 3, 4, 5, 25314. That's sigma. Let's see, tau is another permutation of 5. Say it's this one. I just wrote these down at random. So what is, so multiplication of permutations means composition of functions. So let's try to compute sigma tau. So sigma tau is going to be some permutation of S5. So let's do the calculation. Sigma tau of 1, but this is composition of functions, so this means sigma of tau of 1. Tau of 1 is 5, so this is sigma of 5. Sigma of 5 is 4, so this is 4. So 1 ends up at 4. Sigma tau of 2 is sigma of tau of 2. Tau of 2 is 4. That's sigma of 4. Sigma of 4 is 1. So 2 ends up at 1. Sigma tau of 3 is sigma of tau of 3. Tau of 3 is 3. And sigma of 3 is 3. So 3 gets sent to 3. Sigma tau of 4 is sigma of tau of 4. Tau of 4 is 1. So this is sigma of 1. Sigma of 1 is 2. So 4 ends up at 2. And sigma tau of 5 is sigma of tau of 5. Tau of 5 is 2. So that's sigma of 2. Sigma of 2 is 5. So 5 also ends up at 5. So when you do the calculation, that's sigma times tau. Now, so you have a little bit of practice. Compute yourself right now tau sigma. Right? Let me do the first one and I'll give you a few minutes to do the rest. Tau sigma of 1 is tau of sigma of 1. Sigma of 1 is 2. So this is tau of 2. Tau of 2 is 4. So 1 goes to 4. So compute tau sigma of 2, tau sigma of 3, tau sigma of 4, and tau sigma of 5. And while you're doing that, I will just jot down the attendance so I have it.
Professor, can you move your note down a little bit down? Yeah, thank you.
Let's see. I have two people whose names don't show up on the list of participants. There is Numa D. What is your last name?
Darame.
Oh, right, there you are. Good, thank you. And Nil, N-I-L, who are you? Nil? Okay. So, did someone calculate what the permutation tau sigma is? What numbers go across in the second line here after the 4?
I got 4, 2, 3, 5, 4.
Let's see. Let me just double check. So tau sigma of 2, that's tau of sigma of 2. Sigma of 2 is 5, and tau of 5 is 2. Tau sigma of 3, tau of sigma of 3, sigma of 3 is 3, so that's tau of 3, and that's also equal to 3. Tau sigma of 4, tau of sigma of 4 is tau of 1. Tau of 1 is 5. And tau sigma of 5, so that's tau of sigma of 5. Sigma of 5 is 4, and tau of 4 is 1. So this is 4, 2, 3, 5, 1. And if you compare sigma tau and tau sigma, sigma tau is 4, 1, 3, 2, 5. Tau sigma is 4, 2, 3, 5, 1. So this is, again, another observation of the fact that sigma tau is different from tau sigma. So Sn is a non-abelian group. The order of multiplication matters a great deal. You can't just multiply carelessly. The order of sigma tau and tau sigma are very important. Okay. Part of the next homework is to write a permutation as a product of cycles. So let's just do some example, another example of how you do that. So let's take a big permutation. Let me write down numbers. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All right. So this is my permutation. Sigma. So I want to decompose sigma into a product of disjoint cycles. So let's just start and follow some numbers around. So if I take 1, 1 goes to 2. 2 goes to 5. 5 goes back to 1. That's a 3 cycle. 3 goes to 11. And 11 goes back to 3. That's a 2 cycle. 4 goes to 10. 10 goes to 7. 7 goes to 6. 6 goes to 13. And 13 goes back to 4. So I have 1, 2, 3, 4, 5, 6, 7. What about 8? I haven't used 8 yet. 8 goes to 9. 9 goes to 12. And 12 goes back to 8. So this is sigma as a product of disjoint cycles. Here we have a 3 cycle, a 2 cycle, a 5 cycle, and a 3 cycle. And these are disjoint. Another name for a 2 cycle, 3 goes to 11, 11 goes back to 3. This is also called a transposition. And these cycles are disjoint. And I should also make the following observation. Disjoint cycles commute. So if you have alpha equal A1 up to AK, a K cycle, and beta B1 up to B sub L, an L cycle, and these are disjoint. So all the numbers AI are different from all the numbers BJ, then alpha times beta equals beta times alpha. So for disjoint cycles, the order you write them doesn't matter. Alpha times beta equals beta times alpha. And we actually have a kind of uniqueness theorem that says every permutation has a unique representation as a product of disjoint cycles up to order. Since disjoint cycles commute, whether you write alpha beta or beta alpha doesn't matter, but the cycles are always disjoint. These are disjoint cycles. So that's one of 2 important ways to represent a permutation. Another, which is very interesting, is to break everything down into the simplest possible things. So suppose we have a 3 cycle, like 1, 2, 3. One goes to 2, 2 goes to 3, 3 goes back to 1. I claim I can actually write a 3 cycle as a product of transpositions of 2 cycles. So there are lots of different ways of doing this, and let me do it the way I do in the notes, which is one, 3, 1, 2. This is a product of the transposition 1, 3 and the transposition 1, 2. So let's just check that this is correct. So if I take 1, 3, 1, 2, what does this do? This sends 1 to 2, and this sends 2 to 2. So the product of these two transpositions, 1 goes to 2. This sends 2 to 1, and this sends 1 to 3, so 2 ends up at 3. This sends 3 to 3, and this sends 3 to 1. So in this transposition, in this product, 1 goes to 2, 2 goes to 3, 3 goes to 1. They're exactly the same. So this is a true statement. And there's nothing special about the numbers 1, 2, and 3. If I had a 3 cycle, A1, A2, A3, I could write this as A1, A3, A1, A2. This sends A1 to A2, A2 to A1 to A3, A3 to A1. Yep. So this is a true identity. What about a 4 cycle? A1, A2, A3, A4. I claim I can write a 4 cycle as a product of 3 transpositions. A1, A4, A1, A3, A1, A2. Let's check. This product sends A1 to A2, A2 to A2, A2 to A2, A1 stays at A2. This sends A2 to A1, this sends A1 to A3, and this sends A3 to A3, so A2 goes to A3. This sends A3 to A3, A3 to A1, A1 to A4. So A3 goes to A4. And A4, A1, A4 to A4, A4 to A4, A4 to A1. So 1 goes to 2, 2 to 3, 3 to 4, 4 back to 1. So this is another true identity. And this works for for cycles of any length. So if I have A1, A2, A3, A sub k minus 1, A sub k, this is a k cycle. I can write this as a product of transpositions A1, AK, and just sort of working backwards, always with A1 and then these numbers going backwards. A1 comma A sub k minus 1, A1, A3, A1, A2. So this is a general formula for writing a cycle as a product of transpositions. This is not the only way to do it, but it's a way to do it. And so now we have 2 computational problems with permutations. Given a permutation, write it as a product of disjoint cycles, and write it as a product of transpositions. let's see. I can't use 3 2 times. Two. So this is a permutation in S8. How do I write this as a product of disjoint cycles? So I just start with, I can start anywhere. I'll start with 1. 1 goes to 5. 5 goes to 6. 6 goes back to 1. That's a 3 cycle. Let's see, 2 goes to 4. 4 goes to 3. 3 goes to 7. 7 goes to 8. 8 goes back to 2. So my sigma is a product of a 3 cycle and a 5 cycle. And I can write the 3 cycle as a product of 2 transpositions, 1 6, 1 5. And I can write the 5 cycle as a product of 4 transpositions, 2 8, 2 7, 2 3, 2 4. So here we have just transpositions, which I should emphasize are not disjoint, right? I mean, I have 1 occurring twice, I have 2 occurring 4 times. The transpositions aren't disjoint, but they are transpositions. So this is a basic problem bound to be on every algebra exam you take, which is given a permutation, decompose it into a product of disjoint cycles, and write it also as a product of transpositions. So maybe just as one more bit of practice before we stop. Okay. So there's a transposition, there's a permutation in S10. Write this as a product of disjoint cycles, and then write the cycles as products of transpositions. So I'll give you a few minutes to work on this, and then I'll write it out myself. Someone asked about the notes. So I spend a lot of time writing up the notes and posting them on Blackboard. You also have the video recording of the lectures. So, but what I can't do is like put these notes on Blackboard. There's no reason to, because everything in the notes is in the printed notes that I've posted that are extremely legible. So that's the place to go to learn this, as well as the book by Alan Clark that I recommended, that I included. Okay, so how do we write this as a product of cycles? So 1 goes to 8, 8 goes to 7, 7 goes to 6, 6 goes back to 1. That's a 4 cycle. So pick any number that I haven't used yet. I could start with 2, but I don't know, let me just pick 10. There's no reason, I can start anywhere. 10 goes to 3. 3 goes to 9. 9 goes to 2. 2 goes to 5. 5 goes to 4. 4 goes back to 10. So this is a 4 cycle and a 6 cycle. And how do I write this as a product of transpositions? 1 6, 1 7, 1 8, and then 10 with each of these going backwards from the right end. 10 4, 10.5, 10.2, 10.9, 10.3.
Hello, Professor?
Yeah,
Okay, so basically just to do this type of problem, so let's say, for example, how you started with 1. Just keep going and following what number is mapped to each number until you get back to 1. And for this question, it was 6, so you stopped at 6. And then you can pick any other number, it doesn't matter in particular order, like you did with 10.
Yeah.
And all you did
and
was
you can start anywhere. I mean, I could have started with 7.
Okay.
7 goes to 6. 6 goes to 1. 1 goes to 8. 8 goes back to 7. Now, you might say, and then I can have the rest. You might say, well, these are different. But this cycle, 1, 8, 7, 6, and 7, 6, 1, 8, they're exactly the same permutation. Because this sends 1 to 8, this sends 1 to 8. This sends 8 to 7, this sends 8 to 7. This sends 7 to 6, this sends 7 to 6. This sends 6 to 1, this sends 6 to 1. So even though they have a superficial difference in appearance, these two are exactly equal. These are functions, and they're exactly the same functions. They're exactly the same permutations.
Gotcha. Okay, so that makes sense. And then when you did it with the 2 cycles, when you broke it down, all you did was start with your starting number and then paired it with the number starting from the right backwards, right?
Yeah. So there are lots of ways to write a cycle as a product of transpositions. I'm just giving you one way, but it always works, and you only need one way. So that's fine. And if you have another way to do it, that's also fine. But I gave you one algorithm, one formula for writing any cycle as a product of transpositions. And there are other formulas, other ways to do it. That's not unique at all.
Okay, yeah, no, this makes sense.
Professor,
Yeah.
Professor, yeah,
Yes,
what
sir.
do you mean when you say the transposition is not disjoint?
Well, cycles are disjoint if they don't have any numbers in common. So for example, and the same with transpositions. So 1, 8 and 10, 4 are disjoint because these numbers are different from these numbers. But 1, 7 and 1, 8 are not disjoint because the number 1 occurs in both of them.
Oh, okay, I see. I see now.
So sets are disjoint if they don't have any elements in common. And if you have 2 cycles, you take the set of numbers in one and the set of numbers in the other. And if those sets are disjoint, then the cycles are disjoint.
Mhm. Thank you.
Okay. All right, so so we did a lot today about permutations, and they're very important. And on Wednesday, I will talk about the other important class of non-abelian groups, and those are groups of 2 by 2 matrices. Again, this is all in the latest version of the notes I uploaded to Blackboard. And, you know, the more you can read in the notes, the better, obviously. And then there's homework for next week, which involves permutations. Actually, just permutations. So the homework that's due, actually, it's not next week. Homework that's due on Friday of this week is homework on permutations. And there'll be homework for next week that involves matrices, groups of matrices. Okay. All right, well, if there are no more questions, then we are